Hello and welcome to another continuation of an existing episode of How to Understand X. Today we're going to be continuing our conversation on series. Where we left off, we went over how series works, like a few common series, namely the p-series, geometric series, divergent and convergent series, especially the harmonic series, and we talked about what alternating series are. And we also went over a couple of tests that we are able to use, such as the nth test for divergence, or the nth term test for divergence, in which you just take the limit as it approaches infinity of a sub n, and you try and see whether that equals 0 or not. We also went over the p-series test, the integral test. Well, the p-series test is a corollary of the integral test. And, yeah, I think... Oh, we also went over the alternating series test. So now let's talk about some more general tests that are slightly more difficult to prove, but they just make sense when you sort of think about it. And the first test that I'm going to do is, or at least show, is the ratio test. So again, we're going to be working with some series from usually, well, it doesn't have to be n equals 1. Let's just say we're working with a series, a sum of sequences, or the sum of terms in a sequence of a sub n, right? And if we set this L, or a limit, to the limit as n approaches infinity of the a sub n plus 1 over a sub n, then if the limit is less than 1, we have something that absolutely converges. We have if L is greater than 1, then it diverges. And if L is equal to 1, then it is inconclusive. So this is a bit of an easy idea to understand, but hard to really prove. But we're gonna do our best. So let's work through all of the parts of this. The limit, or L, is equal to the limit as n approaches infinity of the n plus 1th term over the nth term. So that means that every subsequent term is a fraction of the term that came before if L is supposed to be less than 1, right? And if L is equal to 1, or if a sub n plus 1 has the same value as a sub n in terms of the n behavior, then you're gonna have something that cancels out. You'll get an inconclusive value. The reason why this test works is because this only works for absolute convergence. The reason this is inconclusive and not, convergent or divergent is because you don't know if it conditionally converges or not, because since we are taking the absolute value, again, as we said, as we defined absolute convergence in our previous video, we said that absolute convergence is when if you take the absolute value of every single term and add up all the terms in the sequence, you still get a value, like an actual real value. That's what we called absolute convergence. Even if you took the absolute value of every single term and summed it up, you would still get a series that converges. And conditional convergence, which may or may not be this inconclusive, conditional convergence essentially says that if you take the if you take the absolute value, then it may or may not converge. If you take the absolute value of every single term, it will not converge. But if the series is by itself and you did not modify it anyway, usually it'll be an alternating series. Alternating series, series, I need to find a good plural form of series. I'm gonna just say series, but it's a little bit off for me. It might be series I, but conditional convergence. Back on topic, we have conditional convergence is alternating series. If you have a sequence that alternates, but every term is less than the term that came before it, that series is diverging, as we said in that previous video how the alternating series test works. But that is conditionally convergent for specific alternating series. For example, the alternating harmonic, or negative 1 to the n plus 1, if we want to start at n equals 0, or n equals 1, and then go on from there. 1 over n, this is an alternating, like it's going negative 1 to 1 to negative 1 to 1, so there's an alternating value between negative 1 and 1, and this is a harmonic, which means that the denominator is incrementing by 1, and this series actually converges. It conditionally converges because, well, every value is less than the value that came before it. If you just ignored the alternating part, right, just focused on the a sub n, which is 1 over n, every term is less than the term that came before it, and there is an alternating part. That was what we said the alternating series test was. So it is conditionally convergent. But that will not work for this ratio test. If you we'll show an example in a second after we prove it, but if you plug in that alternating series into this, you're going to get 1, because, the limit as n approaches infinity of n plus 1 over n is 1 after you do L'Hopital. But, yeah, if you have L equals 1, it can still be convergent, but it'll be conditionally convergent. And it can also be divergent. For example, if it was just 1 over n, if you were doing, say, the limit as n approaches infinity of 1 over n plus 1 divided by 1 over n, so just times n, you'd still get 1, right? And if a sub n plus 1 is 1 over n plus 1, then a sub n is equal to 1 over n. And the limit as n approaches infinity of this, if that equals 1, you would get an inconclusive, right? But we know that the harmonic series diverges. So if L equals 1, you can get a conditionally convergent series or a divergent series. And if L is greater than 1, again, this is sort of like the nth term for divergence. If every term, so if the n plus 1th term, if the n plus 1th term is less than this term, then if you divided, then the nth term, then if you divided the n plus 1th term by the nth term, you're going to get a fraction. You're going to get a value that is less than 1, right? But if L is greater than 1, which means that a sub n plus 1 is greater than a sub n, if you divide a large value by a smaller value, you will still get a value that is greater than 1. Then you are increasing, right? You're adding terms to every subsequent value of a sub n, which means that you are getting closer and closer to positive infinity. So, well, it could be negative infinity, but you are diverging to an infinity. That's why L cannot be greater than 1. And now, I think it's relatively intuitive. Like, if you think about it, if every term is like a mere fraction of the term that came before it, then you're obviously getting very small values the further and further you go. And if you're adding these extremely small values to an already like solidly established series, then you're not really adding anything at all, and the series should be converging to something. But we can sort of prove this, and we can talk about why this test is so important. P-series and geometric series and all those series are nice and all, but you will not always get these perfect series. Is that you can just sort of like say, hey, this converges or diverges because of this little test. You can't just do that, because most of the time you're not going to have sequences that are that easy to tell whether their series converges or not. You won't always get this really nice geometric series or a really nice p-series to work with. So that's what the ratio test is best for. But before we get to that, we have to try and prove this series. So let's say that the series will start at n equals 1, because that's what we've been doing, right? We're going on the natural numbers. And we will assume that this is true. If L is equal to the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. If this is less than 1, that means that this is absolutely convergent, and we will just say that this is true. And we can also acknowledge that if L is less than 1, because L is not equal to 1, right? If this was less than or equal to, then this wouldn't work exactly. But if you have L is less than 1, then L is, by definition, some value away from 1, which means that there is another value in between, R, right? For example, if you think of L as, say, 0.5, if 0.5 is less than 1, which is true, there can be a 0.75, and you can decrease the distance between L and 1 as much as you want, but there will always be some distance between them, and you could just divide that distance by 2 and say that the distance is R. Right, so, yep, there is an R in between this. So now we have L is less than R, right? And if there is a number, like a value of n that we plug in, if there is an n where the actual n, like the thing that is approaching infinity, is greater than or equal to the nth term, then you would have this inequality, right? So we're just plugging this straight in. If we said that L is equal to this limit as n approaches infinity, we say that this limit as n approaches infinity of a sub n plus 1 over a sub n is less than R, right? And from here we can just multiply, well, 1 second, this does not have the limit added just yet, because, let's see, I'm just looking at this proof right now. The limit is not included because this is n is greater than or equal to n, right? Like this is, the nth term, or the capital nth term, is picked such that the n behavior, or n approaching infinity, is greater than or equal to the nth value that we're on. So, yeah, the L, which is a sub n plus 1 over a sub n, is less than R, which means that the absolute value of a sub n plus 1 is less than R times a sub n. Right, we can put those absolute values again. And again, we said that n is less than or equal to n. N being the, like, number of terms, and this is approaching infinity, and n being a specific number, like a specific term value. So we agree that a sub n plus 1, the absolute value, is less than R times a sub n. So let's plug in this capital N, the actual value. Again, lowercase n is the number of terms, capital N is just a specific n that we have picked, such that, oh, whoa, sorry. This is n is greater than or equal to capital N, because, you can't have a term that is greater than the number of terms. So, yep, my fault. We have n is greater than or equal to n, and so we have this n picked out, and we're going to say that the absolute value of a sub n plus 1 is less than R times a sub capital N, right? And if we acknowledge that a sub n plus 2 is less than R times a sub n plus 1, this implies that this is less than R squared times a sub n, right? If we multiply, well, not if we multiply, if we just think of every subsequent term that comes before it, like if we acknowledge that this is true, then this has to be true, right? The n plus 2th term is going to be less than R times the n plus 1th term, and this is going to be less than the capital nth term, because if, okay, let me break this down just a little bit. So let's split this into two separate inequalities. We have the absolute value of the n plus 2th term is less than r times the n plus 1th term, right? This is just adding an extra term value, and since n is arbitrary, it can be truly anything. So if this is true, then this has to be true, right? And since this is an inequality, anything that we do to one side, we can do to the other side. So if we multiply this by r, we can also multiply this by r, and this inequality would still hold up. So we can also say that r times a sub n plus 1 is less than r squared times a sub n, right? And then from here, we can combine these two inequalities. So let's just write down our thought processes so far. We have a sub n plus 2. A sub n plus 2 is less than r times a sub n plus 1, which is less than r squared times a sub n, right? And we can just continue multiplying this by terms of r and applying the same idea that we applied for previous ones. We can say that a sub n plus 3 is less than r times a sub n plus 2, which is less than r cubed, or, well, it's going to be r squared times a sub n plus 1, but we can still acknowledge that r cubed times a sub n. Like, I skipped a term in between here and here, but just, it's important to remember that this is a general, like, trend that we can see as we increase the number of terms, or the term value that we're on. So now we can try and come up with a rule, right? So let's think about what we have so far. We are saying that the n plus 1th term is less than r times the nth term. So if you just increase values of capital N, or the term that we're on, then you just increase the degree of r which we're multiplying to the original term of n. So we can say that this is a... So I'm really hoping this is a pretty confusing proof now that I'm looking at it, just in terms of, like, actually writing it out, because this whole n is greater than or equal to n thing. Just remember, lowercase n is the number of terms, n is just a arbitrary term number that we're on. So if n is like infinity, which is what we're saying, that we're saying that there's an infinite number of terms in the series, then n, capital N, is the first term, or the second term, or the third term. It's like any random value, and infinity is obviously greater than 3. So n is just an arbitrary value. Like, I'm hoping that this makes sense. But you have a sub n plus k, or the n plus kth term, is less than r times a sub n plus k minus 1. Remember, we're just applying this. If we added k to here, we can also add k to here. And, well, technically we're adding k minus 1 to this one, so we're adding k minus 1 to this one as well. And then we also acknowledge that this is less than r to the k of a sub n. Like we said, the second inequality that we chose, we had a two values that were less than r to the third power times a sub n when we were on the n plus 3th term, right? So yeah, a sub n plus k is less than r times a sub n plus k minus 1, which is less than r to the k times a sub n. So for every k value within natural numbers, we can even write this in math terms just to feel good about ourselves. For all k, like k in natural numbers, we have a sub n plus k is less than r to the k times a sub n. Right, I know this looks like gibberish, but the upside down a is for all. K is, again, the value that we said was arbitrary, just like something that we can add to n plus 1 just to facilitate in this proof. And n is the set of natural numbers, and this sort of e thing just means in. So for all k in natural numbers, the n plus kth term is less than the r to the k of a sub n. So now we have this sort of idea down, and let's try and apply this to something that we're trying to prove. So now we have this, I should probably keep that part down. So let's write down a series that we can apply that knowledge with. Now that I think about it, I probably should have just left this part. Okay, I'm gonna erase this part, and then I'm going to write down the idea that we established. We said that a sub n plus k is less than r to the k times a sub n, right? And so now let's look at this infinite series from k is equal to 0 to infinity of a sub n, well, big N, right? We're on some term n times r to the k, right? This is, well, whoops, wrote that wrong. Well, it's the same thing. It's just order of how we wrote it. We have r to the k times a sub n, right? And this is a geometric series. If you think of a sub n as a, and you think of r as r, like common ratio, we have a times r to the k. If you ignore the absolute values for a second, this is a geometric series, right? And if r is in between 0 and 1, then this is a converging series. And apparently I'm supposed to have taught comparison test by now to make this possible, but well, I mean, we already acknowledged this thing, so I don't think the comparison test is super necessary, but let's write this out. So now we have, we're going to be going from the n plus 1th term. Let me write out this. This is a bit of an abstract way of writing this. So we have n is equal to capital N plus 1 to infinity of a sub n, and this is equal to a series from k is equal to 1 to infinity of a sub n plus k, right? This is a pretty abstract idea, but again, we're gonna assume that n is greater than or equal to capital N, right? And n is, like capital N, is just some arbitrary value for this series to be true for. So if we start at the n plus 1th term, and then we sum up from there, then you are summing up a sub n plus 1, a sub n plus 2, a sub n plus 3, and on until you get to infinity, right? And that is exactly what this is saying. If you start at 1, then you're going to have a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3. So let's write out the terms of this and the terms of this just to show you why they're the same. So let's plug in n plus 1 in for n. Right there we have a sub n plus 1 plus a sub n plus 1, which is n plus 2, and then plus a sub n plus 2 plus 1, which is a sub n plus 3, and on and on. And then we go here, we have k equals 1 that's being incremented. So we start at 1, we have this is equal to a sub n plus 1, and then plus a sub n plus 2, right? We're doing k is equal to 2. This is the second term. Then we have a sub n plus 3, third term, and on and on. So we do acknowledge that these series are equal, and this series is convergent. However, since, let me try and think about this. I'll write down what they have written down. So I'm hoping that everything up to this point is relatively intuitive, like it just makes sense once you see it. But now we're gonna get into the more nitty gritty part of this. So, this proof is saying that if you sum up from n is equal to 1 up to infinity of a sub n, this is equal to the sum up to n, the partial sum, up to n, from n equals 1 up to a sub n. Oh, this isn't too hard, actually. No, I confused myself. This is also relatively obvious. So this is absolute value of a sub n plus the sum from n is equal to n plus 1 up to infinity of a sub n. Right? This is just saying that the partial sum up to capital N of a sub n plus the sum from the n plus 1th term up to infinity should be the same thing as n equals 1 to infinity. This is sort of like integral bounds. You know how if you go from, say, a to b of f of x dx, and you add that to b to c of f of x dx, if both of these are the exact same, then you can just eliminate the bounds, because if you just sort of think about it, if you're taking the area under the curve from, say, a to b, and then from b to c, so this part and this part, you're also essentially just taking the area under the curve from c to a. So you can write this as the integral from a to c, or, well, I don't know why I said c to a, it's a to c, of f of x dx, right? So that was an integral rule that we talked about a while ago, and this is the same sort of idea. Since we are only using inputs that are natural numbers, the term that comes, or the number, sorry, the bound is going to be n and then n plus 1, because it can't equal n. We would be double counting a sub capital N. So if this is true, which I mean it is, right? If you sum up to n and then you add up and you add that partial sum up to capital N to the sum from n plus 1 up to infinity, then you're basically summing from 1 to infinity. Then since this is finite, then this is finite. Hold on. Let me think about this. So we said that this, which was the sum from, let's write out what this was equal to. So we said that the sum from k is equal to 1 to infinity of a sub capital N plus k is equal to this, right? The sum from n is equal to capital N plus 1 up to infinity. And we agree that this is convergent. This is a partial sum, right? So there will be a finite value because there's a finite number of terms. So if this is convergent, as we asserted earlier, and this is convergent, then this is convergent. Yes, this is absolutely convergent, right? Again, because we've been taking the absolute values of every single term so far. But since this is convergent, which we said, and this is convergent because it is a finite number of terms and a finite value that we are summing up to, then this will be convergent, right? Two convergent things, when you add them together, you will get one convergent things because there is a finite number of things that you are adding. So, yeah, since we assumed that L, this limit, is less than 1, and this is true, that means that this has to be true. So we have proven that if the limit as n approaches infinity of a sub n plus 1 over n plus a sub n is less than 1, you will have a absolutely convergent series. And now we need to do another proof, sort of. I would say it's not really a proof. It's more just like common sense. But let's think. If we say that a sub n plus 1 over a sub n is greater than 1, that means that a sub n plus 1 is greater than a sub n, which means that we are monotonically increasing, because for every value of n, this should be true. So if we are monotonically increasing, that means that the limit as n approaches infinity of the absolute value of a sub n does not equal 0, which means that the limit as n approaches infinity of not of regular a sub n, regardless of absolute value, is also, I don't know why I'm so addicted to drawing straight lines, but that's also not equal to 0, which means that this diverges. So yeah, this is less of a proof and more just like a conceptual thinking sort of thing. But if we assume that this is true, if L is greater than 1 for this like inequality, then we are divergent. Then we can say that this is greater than 1 still. Multiply a sub n to both sides, and this, if you plug in any value of n and this inequality is still true, that means that every term is greater than, or well, technically greater than or equal to say it's monotonically increasing, but this is greater than fully, right? There's no equal to on this one, so this is strictly monotonically increasing, which means that the limit as n approaches infinity of a sub n is not 0, which means that the limit as n approaches infinity of regular a sub n, regardless of the absolute value, is also not equal to 0, which means it does not fit the nth term for divergence test, which means that we are left with something that is divergent. So if L is greater than 1, diverges. If L is less than 1, then it converges. And again, if L is equal to 1, we have to do more tests. And I hope it makes sense why that works. Again, we'll do a ratio test example just to really, just to sort of prove. So we have 1 over n squared. Wait, is this a good example? Let me think. I'm not sure this is the best example. I'm trying to think of something that's really obviously going to work for us. So let me think. Okay. I'm just going to use one of the examples that they give. This works a lot with factorials, because factorials, if you add 1, well, we'll show something cool with factorials in just a second. So we have this series from n is equal to 2 up to infinity of n squared over 2n minus 1 factorial, right? And we are going to do the ratio test to see whether this converges or diverges. So let's plug in everything that we have. We have the limit as n approaches infinity of a sub n plus 1, absolute value, over a sub n. And this, for this specific series, a sub n plus 1, we're just going to plug in n plus 1 for every area that we see n. So we're going to have n plus 1 squared over 2 times n plus 1 minus 1, absolute value of everything, times, or well, factorial this, times, well, this is, again, division. You're doing a sub n plus 1 divided by a sub n. So we're going to have this be the reciprocal. So we're going to have 2n minus 1 factorial in the numerator, and we're going to have n squared in the denominator. Okay, so let's evaluate this. We have 2n plus 2 2n plus 2 minus 1, so this is 2n plus 1. Right, so we have the limit as n approaches infinity of n plus 1 squared all over 2n plus 1 factorial times 2n minus 1 factorial over n squared. And now, this is what I'm going to talk about factorials. I think I might have talked about factorial in my set theory video. Factorial, it's useful in a lot of contexts, but for series, we're not going to talk about their permutations and like what factorial really means. I know that's a little bit weird for me because I like to talk about what things mean in every context. Oops. But for this one, it really doesn't matter as long as we are thinking in terms of how to compute a factorial, and that is by multiplying. So if we have n factorial, you're going to have n times n minus 1 times n minus 2, and then on and on, right? Up to 1 factorial. Well, technically up to 0 factorial, because 0 factorial is still 1, but that's actually a pretty cool proof, but I don't think it's really necessary for now. But yeah, n factorial is just you multiply the n by 1 subtracted from every like number that comes before, every natural number that comes before. So 2n plus 1 factorial, this can be written as 2n plus 1, right? If we think of this as n, then this is n times n minus 1, or 2n plus 1 minus 1, which is 2n. So n minus 1 times 2n minus 1, and then on and on. But some of you might already notice you have 2n minus 1 is equal to that on and on part that we were talking about here. Well, even though we didn't draw it out correctly, 2n minus 1 times 2n minus 2 times 2n minus 3, and on and on. This is 2n minus 1 factorial, right? And if that is this, because you are getting 2, 0, then you can simply take out the 2n minus 1 factorial and say that 2n plus 1 factorial is equal to 2n plus 1 times 2n times 2n minus 1 factorial. So now we can actually cancel things out. We have n plus 1 squared, n plus 1 squared over 2n plus 1 times 2n times 2n minus 1 factorial times 2n minus 1 factorial all over n squared. And there is an absolute value going off the screen. But just sort of remember, this is what we have so far. So we're going to cancel out these two, right? And then let's think in terms of degrees. So you have, I'm not even going to evaluate any of this just because I want you to sort of think in terms of degrees and limits. So you have, we're taking the limit of all of this, so the actual computation doesn't matter too much. If you expand this, which, I mean, you probably could just do instantaneously, but if you expand this, the highest degree is going to be 2, right? You're going to have n squared, and that is the highest value. And then if you do 2n times 2n, again, ignore the fact that it's obviously 4n squared, you're going to have n squared. The highest degree between this multiplication is n squared. And then this is also multiplied by n squared. So you have a term with a degree of 2 in the numerator, and a term with a degree of 4 in the denominator, right? N squared times n squared is n to the 4th power. And if you do the limit as n approaches infinity, go across this screen and then just go straight to this. If you have the limit as n squared as n approaches infinity of n squared over n to the 4th power, you're going to have 1 over n squared, which is 1 over infinity, right? And that goes to 0, which means that L is less than 1, right? because L is still an absolute value, you will get a positive value for L, but L is less than 1 because L is equal to 0, which means that this series absolutely converges. And I wish there was a way to sort of like prove why it converges, but yeah, like you could just sort of plug this into your calculator. Just go and do like a partial sum up to like 100 or something. You will get a value that is not infinite. And yeah, so. And also, if you just sort of think about how this works, parabolas do increase very quickly, but again, we're going to go back to some of our introductory derivatives. The instantaneous rate of change for x squared, the parent function for a squared function, is 2x, right? So the rate of change is constantly increasing at 2x, and for every x value, the instantaneous rate of change changes for that respective input. But 2n minus 1 factorial is a very, very rapidly increasing number. Like, just to sort of illustrate it to you, I'm going to say this out loud. If you think of 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, which is 2, 3 factorial is 3 times 2 times 1, which is 6, 4 factorial is 4 times 3 factorial, which is going to be 24, and then 5 times 4 factorial, or 5 factorial, is going to be 120. Then you get to 6 factorial, which is 6 times 5 factorial, which we said was 120, so we're at 720. Then you go forward, you have 7 factorial, which is 7 times 6 factorial. This is a little bit harder to do exclusively in my head. I think I'm going to get it wrong when I say 50, 40, but, you know, you go on and on. You are rapidly increasing, and you're not increasing at a constant rate like 2x. You are increasing at increasing rates. You are accelerating. Might be a better way of thinking of it. But, yeah, the denominator is increasing much faster than the numerator to a point where at like a certain n value, you're essentially adding nothing, because regardless of how large the numerator is, the denominator is so much larger that the fraction itself is simply equal to 0. So yeah, just like thinking about that in our head, it makes a good amount of sense. And we can also do another nice ratio test just to prove how, like, that was not an elementary series, right? You saw, well, I'll show another one. You have the limit, you have the series from n is equal to 0 up to infinity of n factorial over 5 to the n. This is not a nice and simple, you know, this is not a nice and simple geometric series. You can't just factor out this n factorial and say, oh, well, it's n factorial times 1 over 5 to the n, and then this converges, so I'm just going to sort of ignore this n factorial and say that since this converges, then the whole thing converges. You can't really do that, and you are not going to be able to have, even these examples are relatively normal looking for quite a few ratio tests, especially with Taylor series that you yourself have to construct. It's going to get very crazy very quickly, right? But for these types of sequences that don't really conform to any established types of sequences that we've worked with so far, that's what you use ratio tests for. So let's do n factorial over 5 to the n, right? So we're going to do the limit is L is equal to the limit as n approaches infinity of a sub n plus 1 over a sub n, right? And a sub n plus 1, we're just going to plug in n plus 1 in for n. You're going to have n plus 1 factorial. I'm going to still keep the limit as n approaches infinity. N plus 1 factorial over 5 to the n plus 1 times the reciprocal. So we're going to have 5 to the n over n factorial, right? And as we said, n plus 1 factorial is the same thing as n plus 1 times n factorial, right? So if we say that this is true, then we can cancel out these n factorials, and then 5 to the n and 5 to the n plus 1, you do, well, exponent subtraction. You're going to have n minus n plus 1 in parentheses, so you're going to have negative 1 at the end, which is 1/5. So you're going to have the limit as n approaches infinity of n plus 1 over 5, absolute value. Regardless, you're going to have infinity, which is unbelievably greater than 1, which means that this series diverges. And again, for a similar reason, though 5 to the n obviously increases at a much faster rate than x squared, at a specific n value, you are going to get to a turning point where n factorial increases much faster than 5 to the n is able to. And yeah, so that is the ratio test, very important. And I would so go for, well, I would go so far as to say it's the easiest test to do. It is work, like it is more math that you were doing than for other tests, but I think conceptually and honestly in terms of canceling, I think it's probably easier than people give it credit for, and it's definitely not too complicated to sort of see why it works. So that was the ratio test, and don't worry, we still have quite a few more ahead of us. Though for these ones, I'm not going to be using formal proofs. I feel like I've said that phrase, not using formal proofs, a couple of times this video. But this is, again, relatively intuitive. I'm just going to sort of draw out little diagrams, and then we can come to our own conclusions. So let's talk about the direct comparison test. So now that we've talked about the ratio test, let's talk about another very important test, and that is the direct comparison test. So the direct comparison test, I'm not sure if I need to write out direct comparison, I think you know how that's spelled. The direct comparison test is as follows. If the series, well, there's two parts to the direct comparison test, but if the series b sub n converges, right, we assume that this converges, and this is true. 0 is less than a sub n, which is less than or equal to b sub n. So what this is saying is that every single term within the sequence a sub n is less than their corresponding term within b sub n for all n. Well, we say for all n greater than n, with n being in n. I know this is confusing, but this is just saying for all number of terms greater than arbitrary value, like we said for the other proof, and that value being a natural number, then the series a sub n converges as well. So if b converges and a is less than b, then a converges. And already that probably just makes sense intuitively, but we also have this second part to this direct comparison test. If b, if b diverges, so the series b sub n diverges, and 0 is less than b sub n, which is less than or equal to a sub n, then the series a sub n diverges as well. And again, this might seem relatively obvious. Like if you try and draw I'm going to draw it as a function, but just imagine this is a sequence, and this is a sub n. So let's say that this is b sub n, and this is a sub n, right? And we're going to start with the converges idea. If b sub n, let's express the sequence of partial sums as just like a function. If b sub n converges, and a sub n, I know I'm writing over it, but if a sub n is less than b sub n, so every single term is less than its corresponding term in b sub n, that means that A sub n converges, right? Because A is less than B. So if B has a value, then A is therefore a value that is less than that. And it's a similar concept for the diverging part. Like, for example, let's try and draw it. If you have this diverges, so let's say that this is, well, that's not the best example. Let's say that this is A sub n, and then this is B sub n, right? And this is, area under the curve, or the series up to a specific value. Again, we're trying to express the sequence of partial sums as a function so that we can actually draw it out like this. If B sub n diverges, right, there's an infinite area under this curve, and every single term of A is larger than the corresponding term in B. If A is therefore greater than B, then since B diverges, A diverges. Like, if you just sort of look at that, it makes sense, Just, you can sort of substitute A as infinity, right? B as infinity. So if we say that B sub n diverges, which, it can oscillate, which is like a different idea, but even then, it's a whole nother can of worms. But if B sub n diverges, it's going to negative or positive infinity, right? Since it's 0 is less than or equal to B sub n, we're just going to stick with positive infinity. So if B sub n, that series, diverges to positive infinity, then since every single term in A is greater than B, A will also diverge to positive infinity. And for the converging part, if B is converging to a single finite value and A is less than that, then the value that A converges to is going to be less than B, because common sense. But, there's no such thing as common sense in math. We need to define everything. So let's try and write a proof. Oh, you can also, since we specify that 0 is less than B is less than A and 0 is less than A is less than B for the converging part, we can also write that the absolute value of A sub n is less than or equal to the absolute value of B sub n, and this converges, then this converges. And this is absolutely converging, right? Because we're taking the absolute value of every single term. So if the absolute value of A sub n converges, if the absolute value of B sub n converges, then the absolute value of A sub n also converges, which means that the series itself is absolutely convergent. And if the absolute value of B is not absolutely convergent, so if B sub n is not absolutely convergent, so it can still be conditionally convergent or divergent, but if we just acknowledge that B sub n is, not absolutely convergent, then less than or equal to A sub n, since every term in this is greater than this, it could still conditionally converge. If there was an alternating part, then perhaps A sub n and B sub n might both conditionally converge, but this absolutely converges if this converges, and if this, if this is not absolute convergence, then this is also not absolutely, I'll just absol converging. So again, it can still conditionally converge. It can still diverge, but it will not be absolutely converging. This is slightly less useful, I would say. I think that the 0 is less than A is less than B, and the 0 is less than B is less than A for convergence and divergence respectively is probably slightly more useful, but this is still very helpful for some Taylor series and some ideas in the future that we might have to use. But yeah, absolutely converging in and of itself is a good thing to remember, that if A is less than an absolutely converging series, then A absolutely converges, And if A is greater than a not absolutely converging series, then A does not absolutely converge. And again, this is relatively obvious if you just sort of think about it, but we want to prove it. I mean, to me, I'm basically in a vacuum, you know? Like, I might consider it very simple, but lots of people might not. And I'm hoping that if you just sort of look at this, like, rather, um, you know, messy illustration right here, if A is greater than B and B diverges, you know, you're going to positive infinity, then A will also go to positive infinity. Like, so you're going to have a diverging sum, and, you know, vice versa. If A is less than B and B does converge, then A will converge because A is less than B. So now let's try and use the formal proof. So let's let A, N, like A sub N, be a series, and B sub N also be an infinite series with B sub N converging absolutely. Absolutely. I'll just say there exists A, B, Bn converges absolutely. And we are also going to assume, just for the sake of argument, that A sub n is less than or equal to B sub n for every n value in their corresponding terms for both A sub n and B sub n, right? So let's say that the sum up to n number of terms for A sub n is equal to the absolute value of A sub 1, A2, A3, and on until you get to A sub n, right? Because you're summing up to n, and that T n, so the sum up to n terms for B sub n, or the second sequence, is going to be B1 plus B2 plus B3, and up until you get to B sub n, right? N being just some number. I know we use capital N's for the previous proofs to denote like random values, but still the idea is the same. You're summing up to n for both of these partial sums. So yeah, since B sub n, this converges absolutely, then the limit as n, okay, I'm going to erase this, but I think, you know, you can just sort of think S sub n is the sequence of partial sums up to A sub n, like the nth term, and T sub n is the sequence of partial sums up to B sub n. So if we say that B sub n converges absolutely, then the limit as n approaches infinity of T sub n is equal to T, right? As you are increasing your n value, you are getting closer and closer to the sum, the actual sum. So the limit as n approaches infinity of the sum will be the sum. So pretty simple. And for all n, since these are finite values and each term is greater than 1, you are starting at 1, and you're taking the absolute value, so each value is greater than or equal to 0. We're going to say that 0 is less than or equal to S sub n, which again was A1 plus A2 plus A3, and on until you get to the nth term, and that this is less than or equal to the sum of, well, everything, S sub n plus t, right? So let's try and explain sort of what's happening. If this, okay, I'm going to erase this, but just sort of keep some of this in your mind about the whole partial sums up to t and the limit as n approaches infinity of t sub n is equal to t. Just sort of remember that. We're going to rewrite a somewhat strange way of writing this, but it still makes sense once you think about it. So, if 0 is less than the partial sum up to, or greater, less than or equal to, because I mean, you could have a1 and a2 still be zeros, and it would still be less than, I mean, greater than or equal to 0. So we have a1 plus a2, and then on until you get to a sub n, right? And this is less than or equal to a sub 1 until you get to a sub n, right? So we're still saying that s sub n is less than or equal to essentially s sub n. Let me put the ellipses to sort of say that we have this sequence continuing, plus a sub n. If we have this, and then we add b sub n plus 1, the n plus 1th term in b, and then, on and on. If we said that t sub n was the sum up to n for b, then b sub n plus 1 is what is left. So let's fully think about this. T sub n, we agree, is a partial sum. It is a sum of every term up to n, b1 plus b2 plus b3, but it is not the actual series itself. N is not infinity, at least not yet. We did say that the limit as n approaches infinity of the sequence is t, but the actual series itself goes beyond n, right? Goes to n plus 1 and n plus 2 and n plus 3 because n is a finite value. So t is equal to b1 plus b2, and then I'll do the dot dot dot, plus b sub n plus b sub n plus 1, and then, continue dot dot dot, because it will continue past n. T sub n is just the sequence up to a specific n value. And if we add up, well, if we subtract t sub n from t, we will be left with b sub n plus 1 plus b sub n plus 2 plus b sub n plus 3, and on, right? And this is s sub n. We agree, and we said that t sub n was up to n, and then t goes past n. It goes b sub n plus 1 and on. So this is s sub n plus t, the actual value of the series, minus t sub n is less than or equal to t, right? Because if you add up all of these values and you have the actual value of b, like the actual series that b converges to, and the partial sum up to n number of terms, this will still be less than or equal to the actual t, like the actual value for b, because again, a is for every single term within this series, but within this series, within this sequence, every single value of n for a is going to have a smaller output than the corresponding output for b. That's it. So every term, like a1 will be less than b1, and a2 will be less than b2, or less than or equal to. But because a sub n is inherently less than or equal to b sub n, because that's what we, defined, s sub n plus t minus t sub n will be less than or equal to the actual series for t. So, since s sub n is not decreasing, it is increasing or staying the same. It is monotonically increasing because each term is, I would say greater than or equal to. How do I explain this? So, you are converging to a value. That is true. But you are adding very negligible amounts. I'll just say it's not decreasing. That's a good way of saying it. Because, for these first important, you might even go back to statistics. These are significant values, right? These are okay. Switch to pen. These are significant values. These are the ones that have the most weight on the actual series's mathematical value, and the series takes into account these ones, And as you can see, these are absolute values with addition symbols. You are adding values, so you are increasing, right? But once you get to higher and higher values of n, you will, since b sub n is converging absolutely, that means that this limit, oh, whoa. I'm not going to show the limit notation. Well, I guess I will immediately fold it on that assertion. The limit as n approaches infinity, and the limit as n approaches infinity of a sub n and b sub n. If this is equal to 0, then this is equal to 0 because of squeeze theorem. But since... lost my train of thought. What was I going to say? Oh yeah, so since this limit as n approaches infinity of a sub n is equal to 0, you are getting to very small values for the higher values of n. So while you are not increasing by, more than an infinitesimally small value, you're still not decreasing. So we'll just say that the partial sum up to n for s is non-decreasing, right? And this sequence, this new sequence that we created, s plus t minus t sub n, is non-increasing, right? Because again, b sub n will be, approaching 0 for higher and higher values of n, and this will get closer and closer to 0, right? You are decreasing the distance between the actual series value and the partial sum up to n. So as n approaches infinity, this, we said, becomes t. So t minus t is equal to 0. Not, crying emoticon, but the idea is still the same. T minus t is equal to 0. So you are getting closer and closer to 0, but you're not technically decreasing. Once you get to these higher values of n, t minus t will essentially be 0. And while you are still adding values, you are not decreasing. So we'll say that this sequence, s plus, I know I marked it up a lot, but s plus t minus t sub n is non-increasing. And given some m's and n's, like, random arbitrary values, I might need to keep that up, actually. Oops. Given some m's and n's that are that are arbitrary values, we'll say m n greater than n, the random terms, and these belong to intervals of s sub n to, this value, s sub n plus t minus t sub n. So this is a small interval, right? As n increases, this is getting closer and closer to 0. So you're just basically going from s sub n, like capital N, to s sub n, right? So this is a slowly narrowing interval, and this length, the length t minus t sub n, is decreasing, or approaching 0 as n goes to infinity, right? So s sub n, or the partial sum up to n, which is again what this series is. The series of a sub n, this infinite series, is s sub n as n approaches infinity. So since this is bounded, and since these bounds are decreasing, I will talk about how this works. This is called a Cauchy sequence. But just in our heads, let's sort of think of it like being strangled. I know, intense analogy, but imagine you have, two hands. I probably shouldn't. Let's stop with the strangled thing. Let's just think as this range of values, s sub n plus 1. Let me write down what I'm doing. If we have s sub n, again, n is just some, arbitrary value. This is the interval, or the range of possible values, s sub n to s sub n plus t minus t sub n. As n this n increases, that means that this is becoming closer to 0, right? So this range is constricting, right? You're getting closer and closer to 0, which means that s sub n, which will be the bottom one, and s sub n plus t minus t sub n are getting closer and closer together, which means that you are approaching some value, right? You are converging to a value. And again, you might be thinking, well, this is a sequence, right? S sub n. This is not a series, but you have to remember S sub n in this context is not just a sequence, it is a sequence of partial sums. So you are getting closer and closer to a center value. You are converging, which means that our assertion is true. Since b sub n is absolutely converging, then by all of this mess, S sub n is also absolutely converging. But again, if you don't want to think of it like that, which is totally valid, I mean, this is intense. If you just sort of think of it like, if you have a sequence that is less than less than a converging sequence, that new sequence will converge. And if you have a sequence that diverges and this new sequence is greater than a diverging sequence, then the sequence that is greater than something that is already approaching infinity will obviously approach infinity. So yeah, oh my lord, I would say that this is a very normal thing to think, but since we have to do it in terms of math, it is more annoying, but to actually describe and show. But like common sense wise, if you just ignored math, I think it makes sense. And from here we have, well, this is a bit of a combination of the two. I don't think we're going to be using this very often, but it is something to remember. If b sub n, I'm not going to show the full proof for this one because it's pretty similar to the proofs that we did for both the ratio test and for the direct comparison test. If b sub n converges, and again, b sub n is an infinite series, and a sub n is greater than 0, and b sub n is obviously greater than 0, then, well, it's not obviously greater than 0, but it is converging to a value. And a sub n plus 1 over a sub n is less than or equal to b sub n plus 1 over b sub n for all n, then this converges. This is a bit of a combination of our ratio test and our direct comparison test, but let's sort of think about what's happening here for just a second. If you have b sub n plus 1, so we acknowledge that b sub n converges, right? And we're not saying that it absolutely converges because we don't have absolute values for this inequality. We're just saying that b sub n plus 1 converges. And b sub n plus 1 over b sub n is less than 1, or it could potentially be less than 1. That means that if a sub n plus 1 is less than this already established converging ratio, then a sub n plus 1 over a sub n will therefore be less than this thing that already converges. So it's a similar idea to the comparison test, and it's also similar to the ratio test. Since we established that b sub n plus 1 over b sub n is less than 1 because b sub n converges, that means that a sub n plus 1 over a sub n is less than 1 because it's less than, okay, I'll write down this. That makes it a whole lot easier to see. Since this is less than this is less than this, which means that this converges by the ratio test. And yeah, I'm not going to do a proof of that because it's essentially the proof of what we've done for the past couple months. This is called a ratio comparison test, and if you just apply what you know about the ratio test to the direct comparison test, then this is exactly what's happening, right? And if b sub n diverges, and the reason that a sub n and b sub n are greater than 0 is because you obviously cannot divide by 0. You will not get a value. Then if a sub n plus 1 over a sub n is greater than or equal to b sub n plus 1 over b sub n, then this diverges. Again, if you think of this as greater than or equal to 1, since this is greater than or equal to 1, this is greater than or equal to 1, which means that since this diverges, this diverges. That's the ratio comparison test. It's just applying what you know about the comparison test to what you know about the ratio test, and then restating it. So I don't feel like a proof is strictly necessary, and you're probably not going to use this as often as you're going to do the normal ratio test or the normal direct comparison test, but understanding why this ratio comparison test works is helpful, and I think it also just makes a whole lot of sense. So yeah, I think I might have to do like an example video, just going through each of the tests and going through examples for each of the tests and how they, just getting some examples of diverging and converging series that that either fit or don't fit the tests for convergence that we've been doing so far. But for now, I am just trying to establish the basics and why those basics work. So we're going to go straight into the limit comparison test. So now that we've defined both the ratio test and the comparison test and their derivative, not like derivative, the thing that comes from it, the ratio comparison test, we have yet another thing to compare with. We have the limit comparison test. And this one is also a rather interesting one in my opinion. If you have a series of a sub n and a series of b sub n, right, where a sub n is greater than or equal to 0 and b sub n is always greater than 0 for all n. So I don't think you needed to put for all in there, but it's just like for all n, then if the limit as n approaches infinity of a sub n over b sub n is equal to c, with c being a value in between 0 and infinity, so just a positive finite value, then either both converge or both diverge. So if you pick a divergent b or divergent a, then you'll have a divergent a and a divergent b, respectively. And if you pick a convergent b or a convergent a, you will have a convergent b and a convergent a and a convergent b, respectively. But yeah, the point of this limit comparison test is if you are given an a sub n, because we're gonna just assume that a sub n is what you are working with, b sub n is something that you are picking yourself, and if you say that, hey, a sub n over b sub n converges to a single finite value, then since b sub n converges, a sub n has to converge. And this one I'm actually going to encourage looking at this proof, because for the other ones like the ratio test and the direct comparison test especially, the proofs aren't super important, but this is a pretty, I wouldn't say abstract idea. I think it makes sense. If you say that b sub n is a converging series, right? Let's just assume that b sub n is a converging series, and a sub n over b sub n results in a c, a constant or some real value, some real finite value. That means that a sub n is basically, you know how triangles, there are similar triangles, for example, if the angles are equal, but just you extended the size by, say, this is not an equilateral, but if this is x and you just made it 2x, these are similar triangles because you multiplied by a common factor of 2, right? I would say these are sort of like similar series. If a sub n over b sub n results into a constant, that means that a sub n or b sub n are factors of one another. It's not necessarily a constant, it can be like a decimal or a fraction, but the idea is still the same. You can multiply b sub n, every term in b sub n, by a specific value to get every term in a sub n, and since b sub n converges, a sub n has to converge. That's the idea behind the limit comparison test, but again, a little bit abstract. And this proof is also very, very pretty intense. It's similar to the actual formal definition of a limit. So we've gone over that several times, but it's more like, again, just compared to tolerance, you have to set an epsilon that the limit, well, the function's value minus the actual limit is less than some arbitrary epsilon that is in and of itself a very small value. That's the idea of a limit. And, as x approaches some value within like a specific tolerance, and that tolerance becomes smaller and smaller, then the limit gets closer and closer to the actual value of the function, and that's what the limit is as x approaches a specific value, because the tolerance is decreasing around it. Then f of x is approaching a certain value because the tolerance around f of x is decreasing. But I did talk about that in the limit video. So since the limit as n approaches infinity, we're going to assume, like for this proof, we're going to assume that the limit as a sub n over b sub n, where n approaches infinity, is equal to c. Then for every arbitrary, not 3, for every arbitrary epsilon that is greater than 0, there exists a positive n0, so n0 in natural numbers, a positive integer, such that for all n, so for every term that is greater than or equal to this, n0, this first n that we've described, we have that a sub n over b sub n minus c is less than epsilon. So this is again looking a lot like gibberish, but epsilon is an arbitrary value. This is saying, this inequality is saying that if you, let's rewrite this, or I'll keep it on, but let's just rewrite it off to the side. This is the same thing as negative epsilon is less than, not absolute value, negative epsilon is less than a sub n over b sub n minus c, which is less than epsilon. Again, this is a tolerance, and as epsilon is decreasing, this distance between the two is also decreasing. And a sub n over b sub n is getting closer and closer to c. That's what's happening as epsilon is approaching 0. And since this is true, because again, this is just tolerance, and for every n, so considering we are working with a series that uses natural numbers as inputs, if we have a positive n0, or a first term, such that every subsequent term is greater than that first term, this limit can exist, right? You need to have a first term to have a limit as n approaches positive infinity. So, yeah, we agree. We're just stating that this is true, right? And this is, again, definition of a limit, formal definition of a limit. This is what's happening right here. The idea is this is the actual value of, if you plugged in infinity for n and infinity for like n here, this actual value minus c is less than some arbitrary epsilon, some tolerance. So let's write down this idea out a little bit, or let's just sort of expand this inequality. Let's expand this inequality. So we have negative epsilon is less than a sub n over b sub n minus c is less than positive epsilon. That's what this tolerance is saying. And if we add c to both of these, add c, add c, add c, you're going to have c plus minus epsilon, c minus epsilon over a sub n over b sub n is less than c plus epsilon, right? And again, to isolate that b sub n, we can just multiply it to everything. We're going to have c minus epsilon times b sub n is less than a sub n, which is less than c plus epsilon times b sub n. Now, since C, well, this like test only works if C is greater than 0. Like, remember, 0 and infinity are bounding this C. So since C is greater than 0, we can choose E such that C minus, or not E, sorry, C minus epsilon is a positive value, right? Because we want this to be greater than 0. So if we pick an epsilon that is smaller than C, we can have C minus epsilon be a positive value. So if C minus epsilon is positive, then we can actually, write that, let's ignore this part for just a second. If C minus epsilon is positive, we can divide both sides by C minus epsilon, and we're going to have A sub n over C minus epsilon, right? And if this converges, this is again comparison test. So if we have this inequality now, right? Not absolute value, I'm just sort of drawing lines for no apparent reason. If we have this, like, thing out right now, and A sub n converges, right? If A sub n converges, then B sub n converges, because, again, B sub n is less than A sub n divided by another value. So this is less than a fraction of A sub n. So, of course, B sub n is less than A sub n. So since if A sub n converges, then B sub n converges. And that's proving half of this test. So let's just think about this. If this is true, if A sub n converges, then since B sub n is less than A sub n over C minus epsilon, then if this converges, B sub n converges. So both terms are converging if one of them are converging, right? And the limit is C. There is a real value, as we have stated. And we can also do it with the other half now. So if A sub n is less than C plus epsilon B sub n, and we divide both sides, we're going to have B sub n is greater than A sub n over C plus epsilon. And again, in this situation, C plus epsilon is a value, and B sub n is a mere fraction of A sub n. So if A sub n diverges, then B sub n, or sorry, whoa. That's, I made that unnecessarily complicated. You could just sort of look at this and say this diverges. Like, if A sub n is less than something times B sub n, so A sub n is already less than B sub n, but B sub n is being multiplied by an extra value. If A sub n diverges, then this is obviously greater than A sub n, which means that this is greater than A sub n, which means that B sub n also diverges. So either both of them converge, like for this inequality, or both of them. Whoa, I don't know what's happening, like to me right now. But since both of these converge for this inequality, and both of these diverge for this inequality, the limit comparison test has been proven. And again, this is a slightly kind of weird idea, but let's try an example like we did for the direct comparison test. We're gonna sort of explain. I am going to probably do a larger example video on series, how they work, why they work, etc. But let's try and see if the series from n equals 1 to positive infinity converges or diverges from 1 over n squared plus 2n. So what can we compare this to? We know that 1 over n squared, this n equals 1, infinity, we know that this series does converge. This is a p series, and p is greater than 1. So if this series converges, if we do the limit comparison test and divide this by this and get a finite value, that means that this has to converge. So let's do so. If we say that this is a sub n and this is b sub n, we picked some b sub n, let's do the limit as n approaches infinity of a sub n, so 1 over n squared plus 2n times the reciprocal, 1 over n squared, which is n squared over 1, because we're doing a sub n divided by b sub n. So we're going to have n squared over n squared plus 2n, right? The limit as n approaches infinity of that. And again, we could do L'Hopital's, but just as practice of what we did in the comparison test, I want us to sort of get to the point where we don't really calculate as much as we see what is sort of going on with the sequence as a whole and what values we are converging to. So since these both have the same degree, these will, of course, cancel out. And if you want to do L'Hopital's and get to 2n over 2n plus 2, and then 2 over 2, and then 1, you can, but this limit as n approaches infinity of n over n squared plus 2n is equal to 1. And 1 is greater than 0, which means that this converges. And again, this could also be considered a direct comparison, right? Since n is greater than 0 for all n, right, as we have defined up here, 1 over n squared plus 2n is always going to be less than 1 over n squared, because this denominator is going to be greater than this denominator if n is greater than 0, right? So we could just say that since this converges, then by the direct comparison test this converges, but, you know, for slightly more complicated series, you might not be able to do direct comparison, or you might be able to do direct comparison, but it's just simpler to do limit comparison. But yes, it's not like an edge case or anything. Limit comparison tests do have their role, and it's important to see why it works, where it comes from, and yeah, so let's try and specify slightly more about this limit comparison test. There's also a one-sided limit, right? So the okay. So actually, no, I'm not gonna I'm not gonna talk about that. I feel like that's a little bit too far from what we're doing, but it's basically the same thing. So if you have a limit superior, I didn't talk about limit inferior and limit superior because I'm honestly not too familiar with them myself, but the limit inferior and limit superior of a sequence are kind of like the lower and upper bounds on the sequence, like sort of like range, you know? And if you just specify the limit comparison test to the limit superior or the upper bound, then the limit superior of a sub n over b sub n as n approaches infinity is equal to c, with 0 being less than or equal to c is less than infinity. It can equal 0 because, again, you are doing the upper bound. So if b sub n converges, then a sub n converges. But again, this is a bit more of an edge case, especially for, you know, introductory calculus. I don't think we're going to be doing too many limit superiors or limit inferiors. Yeah, inferiors. So we're just going to roll straight on past those, and we're going to go to yet another very nice test. We're going to do the root test. Again, this is I wouldn't say hard idea to grasp, but this is a little bit, it's a little bit strange. We're gonna try and describe this. So let's see, and let me try and pull up my proof for this. Oh wait, this is also limit superior. Okay. Well, this is gonna be more important for power series. Uh, let's see. I'm not gonna do a proof for this just yet, but I'll just sort of show what it's saying. The limit as n approaches infinity, or the limit superior of the nth root of the absolute value of a sub n. If a sub n is the terms of the series, then this series converges absolutely if this limit, we'll say if this is less than 1, but diverges if it is greater than 1. Again, the proof for this is pretty involved, especially since, we aren't particularly familiar with the limit superior, at least on this channel. So I'm just going to sort of explain with words. Again, the limit superior is sort of like the upper bound of a sequence, and if you have the nth root of some specific term, if this is a fraction, you are decreasing, which means that you are converging to a specific value. But if you are greater than 1, you are diverging because everything is increasing, right? You are getting, if you take the limit as n approaches infinity, where this value is greater than 1, you will not get 0, so it won't fit the nth term test for divergence. But if this is less than 1, then it does fit the nth term test for divergence. It says that test is inconclusive, so it could potentially converge or diverge depending on the situation, but this specific test is saying that it will converge. But yeah, I wouldn't say that we are going to be using this, though you definitely will probably use the root test at a certain point. But I'm probably just going to, if I do talk about the root test, it's going to be mostly in connection with power series and how those work. But for now, I think that is it on terms of the more simple tests. Let's see. Let me check. I think that's good. We can also go through a few comparison test derivatives, just like ideas behind them. And so this isn't really a test, but actually I'm not even gonna mention it. This is listed as a test. If a series is absolutely convergent, then it will obviously converge. Because if you're taking the absolute value and the series does converge, regardless of whether you're adding, whether you have negatives or positives, that means that if you did have negatives and you were actually taking out even more, then you will converge to a real value. And there's also the Cauchy condensation test. Again, I'm just going to sort of explain what's happening with this. So if you say that A is equal to the sum from n equals 1 to infinity of a sub n, and a star is the sum from n equals 0 to infinity of 2 to the n times a sub 2 to the n. If this converges, then this converges. Again, this is a bit of an edge case, but I suppose it does make sense. 2 to the n, a sub 2 to the n is obviously going to be a much larger value than a sub n, regardless of where we started at. And so if this converges, then this converges, right? Because this is greater than that. So this is another application of the comparison test. But again, this is more about Cauchy sequences and bounds. But again, the direct comparison test says that since this series is greater than this series, if this converges, then this converges. And the most important thing about this is that A is less than or equal to A star of, which is less than or equal to 2A, which means that A star is bounded between A and 2 times A, which, accounts for the 2 to the power of n, right? And again, pretty abstract. You might not need to use that too often, but just another application of the direct comparison test. Like, I wouldn't go so far as to say that every single convergence test is based off the direct comparison test or the integral test or the ratio test, like those few like really important tests. But I would say most of them at least reiterate the ideas inherent to those tests and either apply them to larger contexts or just are used for more specific situations. And we have this convergence test. If a sub n converges and b sub n is monotonic, so if this sequence is monotonic and b sub n is bounded, so let's say monotonic and bounded, so it has a lower value and an upper value, then if you multiply every term in a sub n by every term in b sub n, you will get a converging series. And I think this again makes sense, especially if you remember that b sub n is bounded, right? If there is a lower and upper bound, then regardless of what you multiply a sub n to b sub n, you will get a finite value, and you will add these bounded finite multiplications to a already converging series. So it will be a larger value, of course, but it will be a convergent series. And I think that makes a good amount of sense. I'm trying to see what other tests are most important. We did talk about telescoping series, how if you have that b sub n plus 1, b sub n minus b sub n plus 1, right, and you do the sum from 1 to infinity, you start at b1 minus b2, and then you add b2 minus b3, and then you add b3 minus b4, and you go on and on, but the first value is the actual sum of that series because everything else is essentially oscillating, so they're being added and subtracted. You might say, oh, well, that's not converging to anything, but it does because every other term is being canceled, but there is a real value that you have approached from the first term. And yeah, I think that's gonna be it. Just looking at this like list of tests and what I think is important to know. I think that's it probably. Um, hmm. Let's see. So yeah, I would say. Okay, this is another application of a ratio test. So since we've been talking about applications of the direct comparison test, let's talk about an application of the ratio test. If a sub n is greater than 0, and b sub n is a sequence created from n times the ratio between a sub n and the n plus 1th term, and that is 1 is taken from that. If L is the limit of b sub n as n approaches infinity, then if L is greater than 1, series converges, so this converges. If L is less than 1, diverges, and if L equals 1, it is inconclusive for that one. And this might seem strange. I can see why it would seem strange, but if you write a sub n over a sub n, well, if you rewrite this as a sub n plus 1 over a sub n, right, because you have the nth term of the n plus 1th term, right? The term that comes before over the term that comes after. And a sub n should be greater than a sub n plus 1 if we have a converging series. If this is less than or equal to 1 minus b over n, then for every value of n over greater than k, being some arbitrary natural number, then this should ring true, right? And this is just another application of the ratio test. Again, b, you could just derive this from this, right? If you add 1, or, well, technically, you're gonna, flip it and, like, do some algebra, basically. But if you divide everything by n raised to the negative 1 power and, like, change some stuff, you can derive this from this. And for all n's that are natural numbers greater than k, and if b is greater than 1, right, because, again, it is a natural number, then this is just another application of the ratio test. You have n plus 1, which is less than n, because it's less than 1 minus a fraction, which is, of course, going to be less than 1. So a sub n will be convergent, because, it satisfies the ratio test. So, yeah, that's a relatively thorough exploration of some of the first couple of series that we will encounter, series tests that we will encounter. Actually solving these series is a whole nother can of worms, and I did not even get to power series and Taylor series, which I'm a little bit disappointed in it. I thought I was going to get to in this video, but, some of these series, like proofs, they are rather involved, and if I'm being completely honest, I really didn't know what I was doing for some of them. Like, I was learning along with you, if you did in fact learn anything. So, I was about to transition straight into the outro, but I do need to do a album recommendation, and I am unfortunately not like great at pronunciation. Like, I would say for most things I have a pretty good level of pronunciation, but for this artist specifically, like, I can speak Spanish, like I can use like a correct accent relatively frequently, and this is a Portuguese name because this is a Brazilian album. This is bossa nova, like a derivative of samba jazz, lots of flute, very similar to elevator music. If you have like stereotypical elevator music, that like idea within your head, this is what it will sound like. There is this one record. Again, I'm sorry, I feel like I'm immediately going to mispronounce this. It's called Chega de Saudade. Like, that's how I would pronounce it. Well, if this was Spanish, I'd say Chega de Saudade, but, like, this is not. This is Portuguese. Somebody told me that it's like Chega de Saudade, or, like, something, very guttural in pronunciation, but I do not know how. And I'm gonna say João Gilberto, so that's what we're gonna go with. I'm gonna go with Gilberto because I feel like that's easier for me to do. But yeah, this is prime bossa nova. Like, this is genre defining stuff. It is fantastic. Again, I told you instrumentation's like vaguely reminiscent of, a hotel, like elevator lobby music, but it is just such an easy listen. Like, I could put this on doing almost anything and it would thematically fit. Like, I could just walk and put these in my ears and I'm just like, that, it just feels good. It's like almost like you're being seduced. That's the best way of describing what this album feels like. It's like being seduced, but also, like, the person who's seducing you is not, like, cocky and arrogant or like being generally kind of annoying. It's like a gentlemanly sort of like Mr. Darcy type of seduction, very, gentlemanly, proper, and charming. Like it's honestly very charming. Gilberto's voice is very soothing. Forgot the R. Lo siento. This isn't Spanish. This is Portuguese, and I do not understand a single word, but I thoroughly love this album. I think it might be one of my favorite records. Period. Just instrumentation is on point. Voice is, soothing but not overbearing. Instrumentation's impressive, and it's like it's like the definitive bossa nova record. And like that might sound like it's generic bossa nova. You might be like, "Oh, so it sounds like every other bossa nova record out there." I would say that every other bossa nova record sounds like this one because this is the pinnacle of the genre, at least in my opinion. And I would say almost perfect. Given I've only listened to maybe like 5 or 6 bossa nova records all the way through, I would say this is probably I would say this is easily the best of the ones that I've listened to, and probably one of the best within the genre. At least from what I've seen online, that's the general consensus on this. But again, if you like this album, please comment down below. If you learned something, please comment down below. And if you did not learn something, constructive criticism. Well, I need to like drink some water. I am stuttering like crazy. But if you did not learn something, please comment down below. Constructive criticism is always encouraged. And if you're not in the mood for a comment or constructive criticism, then uh you can do some what's it called? Shoot. Do a do some half burpees. Those are pretty fun, honestly. I truly don't like normal burpees. Oh, I actually found a perfect exercise to use for my next outro, but it's like a type of push-up that I've been trying that's really fun. Like it's genuinely like it makes me feel physically impressive to do them, but they're honestly not too hard. But I'll do that for that video. But yeah, half burpees are very fun. They remind me a lot of that sort of specialized push-up where you're just pushing up with your body and essentially trying to jump off the ground. And I don't know. I think it's fun, and I suppose I might be a masochist for that. But again, thank you, and bye.